Hi guys, welcome back to our discussion on infinite series. So in this video, we will discuss about the integral test. We will learn how to use the integral test to determine whether an infinite series converge or diverge. But what is integral test? So according to this theorem, if f is positive, continuous, and decreasing for x is greater than or equal to 1, and the nth term of the series is equal to the function f of n, then the summation of a sub n, where n is from 1 to positive infinity, and the integral of f of x dx from 1 to positive infinity, either both converge or both diverge. Okay, like for example, suppose we are asked to use the integral test to determine whether the given series converge or diverge. So, the first thing that we have to do is to check whether the function is positive, continuous, and decreasing. So, from the given n term of the series, now we can define f of x as x over x squared plus 1. And because the value of x is from 1 up to positive infinity, the numerator and the denominator are always positive. So therefore, the function is positive, which indicates that the function is positive and continues within this range, x is greater than or equal to 1. Okay, next we need to check whether the function is decreasing. So to check whether f is decreasing, we need to find the derivative of the function. And because the function is a rational function, we can use the quotient formula for the derivative. Recall that the derivative of u over b is b times the derivative of u with respect to x minus u times the derivative of b with respect to x all over b squared. So applying this formula, so the derivative of the function f of x is the denominator, which is x squared plus 1, times the numerator, times the derivative of the numerator is 1, minus the numerator, which is x, times the derivative of the denominator, which is 2x, all over the square of the denominator. So you have x squared plus 1 quantity raised to the second power. So simplifying further, this can be written as x squared plus 1 minus 2x squared. Okay, so let's rewrite this. Okay, so you can write this as x squared, okay, plus 1, no, minus 2x squared, all over quantity x squared plus 1 raised to the second power. But x squared plus negative 2x squared, this is negative x squared. And plus 1 all over the square of the denominator, which is x squared plus 1 quantity raised to the second power. So, because as you can see, because the first derivative is negative, let's say for example, if the value of x is 1, this is 0. But if x is 2, so 2 squared is 4, and negative 4 plus 1 is negative 3. And because the denominator is always positive for any value of x within this range, so f prime of x is negative for x is greater than 1. So we can conclude that the first derivative of the function is negative, meaning the function is decreasing because the first derivative is negative or 0 or less than 0 for x is greater than 1. And it follows that f satisfies the conditions for the integral test, that the function should be positive, continuous, and decreasing for x is greater than 1. So because it satisfies the condition, we can now use the integral test. So in integral test, we need to evaluate the integral of f of x dx, where f of x is x over x squared plus 1, times dx, where x is from 1 to positive infinity. So if we let u as the denominator, okay, if you let u, as the denominator x squared plus 1, then du is 2x dx. Okay, but because 2 is missing in the numerator, so there should be a correction factor of 1 half. So this should be 1 half times du, where du is 2x dx, all over u, where u is x squared plus 1. So this is now of the form du over u. And recall that to evaluate the limits of f of x, where x is from 1 to infinity, uh, we can evaluate this by taking the limits because this is improper integral. Okay, because of the infinite limits. So to evaluate the improper integral, we take the limits of the integral of the function 2x over x squared plus 1 dx, where x is from 1 to b as b approaches positive infinity. So we replace the upper limit, which is the infinite limits, by b as b approaches positive infinity. And then after that, because this is of the form du over u, the integral of du over u is u is equal to natural log of u, no, where u is x squared plus 1, evaluated from 1 to b as b approaches positive infinity. Then, by substitution, upper minus lower, we have 1 half times the limits of the natural log of x squared plus 1, where x is b, so this should be natural log of b squared plus 1 minus the natural log of this function when x is 1. So you have 1 squared plus 1 is 2, so you have natural log of 2. But we take the limits of the natural log of b squared plus 1. If we replace b by infinity, infinity plus 1 is infinity, and natural log of infinity is infinity, no, minus natural log of 2 is still infinity times 1 half is infinity. Because the integral of the function x over x squared plus 1 dx from 1 to positive infinity is infinity, so therefore we can conclude that the series diverge. So in summary, we can say that if f is a positive, continuous, and decreasing for x is greater than or equal to 1, and a sub n is f of n, then we can say that summation of a sub n, where n is from 1 to infinity, and the integral of f of x dx from 1 to positive infinity, either both converge or both diverge. So you have to check first whether the integral of the function exists. If it exists, then the series converge. But if not, if the integral does not exist, then we can say that the series diverge.